Alright everybody, welcome to the first of two videos that are going to cover sections 11.1 to 11.2 or anything like that. Section numbers may have changed, but the topic of the video is area formulas for polygons. There are going to be two videos for this. One of them is going to go through the formulas themselves, and the second video is going to go through examples of using those formulas and how we can use them to find values in problems. So let's get started with the formulas themselves. Now, many of the formulas that you're going to see here today are going to be using the ideas of a base and a height. And what you should think of with that is, oftentimes we're going to have, different lengths for these. But let's say that we have this segment and we call this the base. The height compared to that base is going to be sticking straight out of it, and the key is that there's going to be a 90-degree angle between them. They will be perpendicular to each other. So when calculating the area of a polygon, the base and height must be perpendicular. They have to be, otherwise they are not base and height. It doesn't work if they aren't that. So that is how that's going to work. Let's move on to the formulas. All right, first up, I'm actually going to skip area of a triangle for a moment, and I'm going to go straight to area of a polygon, of a parallelogram. So parallelograms, remember we have many kinds of parallelograms. We've got the one that doesn't really have any other defining features, but we also have rectangles, we have squares. In general, the formula for the area of a parallelogram is going to be simply base times height. So whatever the length of the base is, whatever the length of the height is, I kind of switched these here, but you could call either one of them base or height. It really doesn't matter since you're multiplying them. Same goes with regular parallelograms, ones that don't have any special features. The height is that distance between those two segments, and here's the base on the bottom, that length. So area of a parallelogram is just going to be base times height. You multiply those two numbers together. The reason I did parallelogram before I did triangle is because, and this is easiest to see with a rectangle, if I start out with a rectangle whose area is base times height, if I were to cut that rectangle in half, notice that I formed two separate triangles of the same size. The area of that rectangle would be base times height, but when we turn it into a triangle, we're only getting half of what that number would be because it's half of that rectangle. So that gives us the area formula for a triangle, which is we have our base times height, but we only want 1/2 of it. So we have 1/2 base times height, because only half of the area of what a triangle with, or a rectangle with the same base and height would have, or really any parallelogram. Trapezoid is next. And what we want to do for the area of a trapezoid, just as a reminder, here's a trapezoid. So what you're going to want to do for this is this also will involve the height. Height, again, is going to be the distance between the two bases. Notice that that's a right angle there. And remember that in the trapezoid, the bases can be different lengths. So we're going to call the top one B1, the bottom one B2. And when we do that, the way we find the area is we're going to take 1/2 of B1 plus B2. Now, if you think about what that's doing, we're taking the two bases, we're adding them together, and we're dividing by 2. We're finding the average of the two bases for that first part. And then we multiply by the height. And that is the area of a trapezoid. That's all you have to do there. So, next up, area of a rhombus. And you'll notice that rhombus is not included in with the other parallelograms, and that's because the rhombus kind of has its own special formula. Rhombus doesn't quite work like the other ones do, and the reason for that is, in a rhombus, sometimes it's a little bit difficult to think about. If you treat one of the sides as the base, it can be a little bit difficult to figure out what the height would be that would go with that base. So we do something different for rhombus, but the nice thing is, the formula for the area of a rhombus is the same as the formula for the area of a kite. So these two kind of go together. When you have a rhombus, remember one thing we talked about in a rhombus, besides the sides having all the same length, is the idea of diagonals, which is where we go kind of across the shape. And we talked about how diagonals in a rhombus are perpendicular, all that good stuff. Well, remember that in a rhombus and in a kite, the diagonals don't have to have the same length. So let's call one of them D1 and the other one D2. And I'm talking about the full length of it, not just half of it, the whole length of the diagonal. In that case, the area of a rhombus and the area of a kite are both going to be 1/2 of the length of one diagonal times the length of the other one. And again, the same is going to be true for a kite. So they both work the same way, and the diagonals kind of look similar between the two. Remember, the big difference being in a rhombus, parallel lines, all the side lengths are the same. In a kite, there are two pairs of sides that have the same length, but generally very similar shapes. They both have perpendicular diagonals, so this works. Notice, though, that even though we're not using base and height, we are still using two segments that are perpendicular to each other. That's a good thing to notice. So that is all of these formulas, and in the next video we will go through a few examples that use them in our solving of a problem. So see you there.